Okay, just a quick walkthrough of assignment 3 on genetic algorithms. For this, we're going to be using some code that was originally posted to this blog that implements a very simple genetic algorithm in Java. I modified it quite a bit in different ways, but I wanted you to play with this code and get to know it a little bit. So you can either grab the zip file here, download it, unzip it, and bring it into NetBeans or Eclipse and import it or open up that project. It should be set up for both an Eclipse and a NetBeans project. You can also grab it from GitHub. Again, it's created like an assignment. You can go right there to that link, grab that URL, make sure you click on a project that doesn't have any source control, and then you can go up to team, git clone, and then make sure you paste in that URL here, and then it'll download that quickly to your into your NetBeans area and set that up. So this is just a simple code. It has two classes, a genetic algorithm class and a candidate class. The candidate class is just a solution. It has a gene, which is a array of Boolean values that encodes a gene. And we can initialize. We have a constructor here that initializes it. We have a fitness function, and all a fitness function does is calculate how many ones there are in this gene. So for our evaluation and simulation, all we're trying to do is make all the genes turn to all ones. It's very simple. There's a compare to that compares the fitness of these two things and returns value. This compare to is needed for the built-in sorting on collections in Java. So in the GA class itself, we have a number of parameters here set up that we'll be modifying. Then we have a constructor that creates a random number generator and initializes the population and uses and creates a whole bunch of these initial candidates with this constructor here. And adds them all, and so these are all stored into a linked list, for the population of candidates. And then we use this sort method because we can just say collection sort and uses the built-in sort, which actually sorts based on the compare to method in the candidate, which sorts on fitness because that's how we've programmed the compare to work. There's a print method that prints out this, and the produce next generation does most of the work. This actually goes through, selects a population. It's a little strange as far as how it's set up, a little non-standard. So it'll go in and select 4 candidates and then make sure they're not equal to each other, and then it'll have the candidates compete against each other, and depending on the winner of this, so it'll have candidate 1 compete against candidate 2, and then the winner will be the winner of that and stuff. So it has a kind of a simple competition. It's a little different than a classical genetic algorithm method, but it works fairly well. Then it goes through and does some mutation here based on some mutation percentage, and we'll do some mutation. Now, one thing it doesn't do is really any, well, let's get down to the crossover here. So finally, then we do the crossover. And initially, it does a fixed point crossover, but it also has a random crossover possibility that it can use. So rather than always crossing over, having half of the genes go to one place, half to the other one, this randomly crosses over the genes of the candidates. It has a run method that initializes the population and then goes through a number of generations and produces them, and then prints out the final population after that many generations. And then there's the main program that's needed to run this. So when we run this, it'll start off with the initial population. Let me make this a little bigger. And it'll generate these genes of random ones and zeros here. And so, right now, I think it's set up to 10 individuals, and ranks them all by their fitness. And then he evolves them over time, and right now the methods aren't that good, so the fitness only improves to 69. But here's the best solutions. They all look very similar, in this case, after 50 generations. But your job is to then go through a number of questions on this population. Well, so run it initially and answer these questions. Then you're going to be, each one of these things are going to be modifying things like the population size, and running it and seeing how it affects the population, the performance of it. Basically, watch the top fitness after the generations run, and you'll be reporting that. So you just go through these questions, and again, it'll ask you questions. So repeat this with a smaller population size, say a population size of 50 or a population size of 500. Some of them are asking, and so all those parameters are set up here. So the population size is here, the number of generations, mutation percentage, parent use percentage, and generation size is the length of the genes. All those are up here, and you'll be modifying some of those. The last part of this will be some modification of this where we actually switch the crossover. Uh, let's see, where was that again? It's around line 90 in the code. It's in this produce next generation population, which does the thing. So here it's using this fixed point crossover. We're going to switch it to a random crossover where it actually randomly picking genes from each parent and interspersing them. So try that. So this way you don't have to submit the code. You're not actually doing much changes to the code for this assignment. Just submit the answers to these questions in Blackboard here. So, and again, if you download it from GitHub, you don't have to commit and resubmit it there. You just have to submit the answers to the questions. So like here, repeat this with this. How many generations it take to reach this fitness value? Just tell me how many generations. And so just post the answers to these 8 exercises you're doing. Okay, so hopefully it won't be that bad of an assignment for this week, for this unit.